I wanted to work through a problem that involves vectors. This problem involves displacement vectors, and it involves the addition of several displacement vectors. So in this particular problem, we're told that a cyclist travels firstly three blocks west. Then she travels 4 blocks north. And then finally, she travels 6 blocks east. And the question is, what is the total displacement vector from the addition of those 3 stages of her trip? The 3 blocks west, the 4 blocks north, and the 6 blocks east. So the first thing I'm going to do is draw a picture or make a sketch of the vector addition. And then we'll do the calculation of the vector addition. The usefulness of the sketch is that it helps us think about the problem, but it also will help us check our result. So when I make this sketch, I'm going to consider north on my sketch pad here as up, south as down, west is to the left, and east to the right. And I'm going to draw the vectors according to that convention. So the first stage of the trip is 3 blocks west. So here's a vector. I'm going to call it vector displacement 1. Not very original. And that's to the west. Then there's the second stage of the trip. That's to the north. It's 4 blocks to the north, and I'm going to call that vector displacement 2. Again, not very original. And then finally, there's the third stage of the trip, and that's to the east, to the right here, and that is called displacement vector number 3. So those are the 3 stages of the trip, and the overall displacement on the graph is the vector that starts from the tail of the first stage of the trip, so down here on the left, and goes to the tip of the third stage of the trip, up here on the right. And so this vector, I'll call it the resulting vector, uppercase R. That's the overall, the total, the net displacement for the cyclist. And that displacement vector would have some magnitude. I'm just going to call the magnitude R. And it would have some direction. I'm going to call that angle theta R. And we're actually going to calculate R, the magnitude, and theta R, the direction. Okay, so the first stage in adding these vectors to get the total displacement vector is that we're going to write down the individual vectors d1, d2, d3 in x and y component form. They're horizontal, vertical components. They're north, south, and east, west components. And then the second stage will add up the x components of all the 3 vectors to get the resulting x component. We'll add up the y components of the 3 vectors to get the resulting y component. And that will give us the resulting vector in x and y component language. And then the third stage, we're going to rewrite that resulting vector from x and y component language to magnitude and direction language to get the R, to get the theta R. Okay, so what are the 3 vectors in their x and y components? Well, in this case, because the motions were just east or west or north or south, it's relatively easy to write down what the x and y components are. So, for example, for vector number 1, d1. Its x component, I'll call that d1x, is just the minus 3 blocks, i.e. the 3 blocks in the negative to the left direction. And its y component, that's just going to be d1y in my notation, and that's going to be 0 because there was no motion on the first stage of the trip, no displacement, either upwards or downwards, north or south. So that's vector number 1. Same thing for vector number 2. So its x component will be d2x in my notation, and the second stage of the trip was just 4 blocks north, so there was no travel in the east-west x direction. So d2x is 0, but d2y, the second stage of the trip, we traveled 4 blocks north, so d2y is 4 blocks, 4 positive blocks in the northerly direction. And then finally, the same thing, we're getting the hang of this now, for the third vector, d3x, well, the travel for the third stage of the trip was 6 blocks east, so that's positive 6 blocks in the positive x direction, and there was no motion in the vertical direction, so d3y equals 0. And I really think of that as stage 1, step 1 of our calculation. We've now got the 3 vectors in x and y component language. Stage 2, we're going to add them up to get the x and y components of the resulting vector. So the resulting vector's x component, I'll call it r subscript x, is the sum of the 3 x components. So that's the sum of d1x, d2x, and d3x. And likewise, the resulting y component, that's the sum of the 3 y components, so it's d1y plus d2y plus d3y. And so all I have to do is add up the 3x components, 3y components to get the resulting x and y components. So for the x components, let's look here. We got minus 3, we got a 0, and we got a plus 6. And so overall, we get 3 blocks traveled in the x direction. For the y components, let's look here. We've got a 0 plus a 4 plus another 0. So overall, we traveled 4 blocks in the y direction. And that's stage 2 of the calculation. We now know the resulting vector in x and y component language. Finally, we want to calculate the magnitude and direction of the resulting vector. Well, for the magnitude, we can use Pythagoras' theorem. The magnitude is the square root of the sum of the squares of the x and y components. And for the angle, we can use a little bit of trigonometry. The angle theta r is the inverse tangent of the ratio of the vertical to the horizontal components of the resulting vector. Now, before I stick the numbers in here, let me just sketch out on this diagram. Maybe I'll pick another color here, black. These components and how they relate to the magnitude and direction. So Rx, the horizontal component, is this horizontal line here. Ry, the vertical component, is this vertical line here. And so you see how the magnitude of the vector, which is the hypotenuse of this right-angled triangle here, is related to Rx and Ry through Pythagoras' theorem. That's the basis, that geometry is the basis for that relation. And you also see here how this angle, theta r, well, that's going to be the inverse tangent of the opposite side of the triangle over the adjacent side of the triangle. So it's the inverse tangent of Ry over Rx. And so you see also how this geometry here, an arrangement of our y and rx, is related to the angle theta r. So these equations are from my picture of the geometry of the resulting vector and its components. Well, now all I have to do is to feed in the x and y components that we already know. So we've got 3 squared plus 4 squared. So that's actually 9 plus 16, which is 25, and the square root of 25 is actually just 5. So the length of the resulting vector is 5 blocks. And then for the calculation of the angle, it's the inverse tangent of ry, that's 4, over rx, that's 3. So inverse tangent of 4/3, 1.33, and that comes out to be about 53 degrees. And that 53 degrees means it's 53 degrees towards the north, measuring away from the east. So this angle in this corner is 53 degrees. Anyway, that's an example, an illustration of the sort of general procedure for adding together vectors, in which we broke the initial vectors down into their x and y components. We then added together, summed up the x components, and added together, summed up the y components. And then once you got the x and y component form of the resulting vector, we could calculate the magnitude and direction. I tried to highlight when we calculated the magnitude and direction that those equations for the magnitude and direction for r and theta r are nothing other than the geometry, the equations that describe the geometry of that right angle triangle, Pythagoras' theorem, and the trigonometric relationships between angles and sides of a triangle.